Yeah, all right. Okay, conservation of momentum. All right, so the law of conservation of momentum is this one here. The total momentum of any closed system is constant and is not affected by the interaction of any parts of the system. So that means if two bodies collide, the total momentum of the system before the collision is the same as the total momentum of the system after the collision. Okay, so the momentum is conserved before and after an impact between the two bodies. Okay? Okay. So that's written here. The momentum before is equal to the momentum after the collision. This is very important. This rule right here trips everyone up. Well, not everyone. Trips a lot of people up every year. It's so important that you define a direction as positive and that you remember to put the negatives in when it's the other direction. Okay, it's just so common that people forget this, particularly in momentum. I don't know why, but it stuffs a lot of people up. So that's that. Okay?
Yes. Yes, sir.
Is this the first example you've got in your book?
Yep.
Fantastic. I love it when the slide matches the book. All right, let's have a go at this first conservation of momentum question. A car of mass 600 kilograms travels north at 16 meters per second. It collides with a stationary car. Hang on. It collides with a stationary car of mass 900 kilograms. If the cars coalesce, one of those, they stick together. So that means that you've got your two bodies, a collision happens, and then they are one body. Yes? They are one body. Right? So we've got different ways. In these conservation of momentum problems, there's pretty much three different scenarios. You can have two bodies, there's a collision, and then they separate, and they're still two bodies. You can have two bodies, they have a collision, and then they are one body. They connect, they stay connected. And the other one is that they are initially together, and then from some impact, they are separate. So that might be confusing, but for example, if you're looking at a gun and a bullet, you've got your gun, you've got your bullet, and they are one body until the gun fires the bullet.
Why is the bullet around the gun?
Because I can't make a smaller fist than the size of my fist. All right, and I didn't pre-plan this. Okay, we're not shooting anybody. All right. So in this example, we've got the two cars. They stick together after the impact. Okay, and you'll see this word a lot, so I should be able to pronounce it. Coalesce. It's an E. It's got to be an E noise. What?
I don't know. I'm just throwing out.
Let's look on the Google how to pronounce that later.
It's coalesce.
Coalesce.
Yeah. No, I like mine, but
It is coalesce.
coalesce.
No, I believe you. It's coalesce. Okay, they coalesce, but I've been saying coalesce all these years. Thank you. Thank you so much. Love that. All right. Now I'm going to pronounce it correctly for the rest of my life. All right. Calculate the total momentum before the collision. Ready? Okay, so what is the symbol for momentum? Above the line or below the line? Okay, good. P. Now, before the collision, we need to put a little letter to show that we mean before. We usually don't use before and after. We use initial and final. So we do a little I. And I normally do I-N-L, but I stopped doing that because people didn't like writing three letters. INL for initial. Anyway, so PI equals, now this is the total momentum, okay? So it's the momentum of the first car plus the momentum of the second car. So let's say P1 plus P2, where this one is the first car and this one is the second car. Okay? All right, so that's going to be, obviously, P is mass times velocity. So it's going to be the mass of the first car times the velocity of the first car. And the other one, mass of the second car times velocity of the second car. Okay, so let's substitute the values in, yes? Okay, what is the mass of the first car? Shh. What is it? Thank you, Jacob. What's the velocity of the first car? What's the mass of the second car? What's the velocity of the second car? Okay. What does that give me? 9,600. And what, do we remember what the units are for momentum? Newton seconds, yes, but I don't want to use that because we've done mass times velocity, so I'm going to go the other one, which is kilograms meters per second. In what direction? So which direction have I defined as positive? Okay, let's pretend I did that at the start of the question, not right now. North positive. What is the total momentum after the collision? Who can tell me that? Very good. The whole idea is that momentum is conserved. P final equals P initial due to the law of conservation of momentum, which you may see written as LCM. All right, so if you're writing an answer and you want to write due to the law of conservation of momentum, you can just write LCM, by LCM, blah, 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 blah. Anyways, so therefore the final momentum of the system is 9,600 kilograms meters per second north. Okay? Is everybody happy with that? All right, what is the velocity of the wreckage immediately after the collision? So we know that the final momentum is 9,600 kilograms meters per second north, right? And what else do we know? We know that the final momentum is made up of the mass of the system times the velocity of the system. Now, because they've coalesced, that doesn't feel right. Because they've coalesced, they are just one body now, yeah? So we don't need MV plus MV again. We're just counting them both as one. Does that make sense? So what is the mass of the two cars put together? What is it? 1,500? Okay. Times by the unknown velocity, which is what the question's asking for. And I can also substitute in for the final momentum because it's just that, isn't it? So that's a straight division. 9,600 divided by 1,500 is 6. That's not... I need more. Thank you so much. Appreciate that. 6.4 meters per second. I got a positive answer. What direction? How do we feel about that so far? Okay. People really struggle with these questions. I'm not really sure why, but they must be difficult based on that. All right. Next. Was I too quick? All right, here we have two ice skaters. Abigail and Bertrand. Poor Bertrand. And they're ice skaters. They've made them ice skaters so that we can pretend there's no frictionless surface. And they are stationary and facing each other. How sweet, okay? And then Abigail pushes Bertrand. So he moves. No, well, they're nice. It's fun. It's fun. It's all fun. So he moves away. Calculate what happens to Abigail. All right. So in this case, Abigail and Bertrand are standing together. It doesn't really matter whether we think of them as one body or two, but anyway. Let's get into it. So I first need to calculate the initial momentum. I can do that because I know both their masses and both their velocities before the collision, right? I don't have enough information to calculate the final momentum because I don't know Abigail's final velocity. Does that make sense? So first I need to find the initial momentum. So PI for initial momentum is going to be the mass of the system times the velocity of the system. The mass of the system is their masses, which is 150. What's their initial velocity? 0. Okay, so the initial momentum is 0 kilograms meters per second. Therefore, what is the final momentum? 0. So that also equals the final momentum. Now, after the collision, we've got P final. Now, they're separate now. We've got the mass of Abigail times the velocity of Abigail plus the mass of Bertrand times the velocity of Bertrand. Okay? So, what am I substituting in for PF? 0. What is the mass of Abigail? 60. And we don't know her velocity, do we? That's really what the question is asking. Calculate what happens to her. I need to define a direction as positive. What do you want? Really? Okay, west is positive. No worries. All right. What's the mass of Bertrand? And is it? No, it's not.
90 kilograms for an ice skater. That's a bit much.
Is it?
Yeah. Average weight is like 85.
I'm Googling it.
And an ice skater
We digress.
pretty light.
Right. Yeah, because otherwise they fall from house. That's why I can't.
Bit rude calling people chonky. Okay. Okay, so Bertrand only weighs 90 kilos. What is his velocity? 1.5. And that's positive, isn't it? Because it's west.
Let's look at the beholder of all knowledge.
Okay. So 0 equals 60 times the velocity of Abigail. What's 90 times 1.5? It's going to be 135?
Yes.
Shh. Oh my God, stop it. What are you Googling the average mass of an ice skater? Oh.
161 pounds. Pounds is about double, so. Get your actual. What if it's just random people at an ice rink?
Yeah, exactly. They might not be professional ice skaters. Oh my God, you guys. All right, let's subtract. Let's subtract the 135 to the other side so we can get the velocity of Abigail by itself, yeah? So we get...
weight is 73 kilos.
Language. All right, now let's divide through by 60. And what does that give me?
-2.25.
Is this what you said?
Mm.
2.25?
Yeah.
What are you eating?
Twinkies.
Huh?
Chicken Twinkies.
What does my negative answer indicate? East. So 2.25 meters per second east is what happens to Abigail. Okay? Does that make sense? So they're standing stationary. Abigail pushes Bertrand, but silly Abigail, hopefully she didn't think that she would just stay in the same position.
Pushing fucking Bertrand and chomping ice cream.
All right, so that is that example. Did we enjoy that one? I enjoyed it. May I move to the next slide?
Two railway carriages approach each other. I slightly agree. 50 tons of human flesh on board.
Okie dokie. I have trouble making the right sounds with my mouth sometimes. You probably noticed. All right. Shh. Stop that now. Two railway carriages approach each other. Carriage P has a mass of 50 tonne. What is that in the old kgs?
50,000.
Yep. Is travelling at 3 meters per second, and Q is travelling at 4 meters per second. Oh, one's going north, one's going south. So P's going this way north, and Q's going south. Oh, okay, so here we go. They're going like this, and then they crash, and they coalesce.
Whoever writes these questions is a bad person.
What? There's probably nobody on board.
It's a train.
Train can carry, it's a cargo train. It's a cargo train. I don't know.
Cargo train's probably worse because they're probably going to do environmental damage and make sure it's like wildlife.
Well, lucky it's hypothetical then. All right.
Train carrying so much oil.
Now, we have a north and a south here, don't we? So what do I need to do first? And which one would we define as positive? North makes sense, doesn't it? South. Why would you have south as positive? Like what? Okay, north is positive. What do I do first? Initial momentum. Thank you. Good. Yes, I first calculate the initial momentum. Okay, the initial momentum is the mass of P times the velocity of P plus the mass of Q times the velocity of Q, right? All right, so let's substitute stuff in. The mass of P is 50,000 and the velocity of P is 3 meters per second north, so that's positive 3. The mass of Q is 75,000 and the velocity of Q is 4 meters per second south, negative 4. See how important these negatives are? If we didn't have that negative, the answer would be very wrong.
Well, it's not like you get it right.
Anyways, what does that make? That whole thing. Plus
150,000. What? That is a lot.
Yeah, that's right.
1,200,000.
You're all telling me different numbers. Negative 150.
Yeah. Or just
And then what?
1,000.
Like 10 years.
I got 1,000.
Is that what you got, you guys?
Sure.
Oh, looks, it can't be million. Sorry. I just don't see how it could be. All right. Good. Good job, everybody. So therefore, my final momentum is the same. Okay? Fantastic. If the carriages coalesce, what is their resultant velocity? Well, it's a big F, not a big P. So, the final momentum is the mass of the system times the velocity of the system, just one m, just one v, because they've coalesced, yeah? Yeah. All right, so we get negative 150,000 equals, what's the mass of both of the carriages together? Yep, times by the velocity. Now let's divide through. 150 divided by 125. What does that give me? I should just get my own calculator, shouldn't I? But 1.2. It's not very fast, is it? Meters per second. And what do I do now? How? Did anyone say no? What do I do now? Is that my final answer? Yes? We have to... So what does that mean? Yes, we interpret the sign as a direction. What direction is negative? All right, so there you have it. One going north. Who said west? Who tricked me? Was that you?
I didn't say
Someone tricked me. I'm like, yes, west. Thank you, west. Yeah, so they're going, one's going north, one's going south, but the south one's heavier and it's going faster, so it's got greater momentum. So it hits it and then they both go that direction, but more slowly. You know?
Yes.
Okie dokie. Of course it is. What else would you expect? All right, my loves, last one. Well, maybe it will once we've done it.
But no, it doesn't make any sense because they're both traveling east, but when they collide, that one bounces backwards and goes west. So, I mean, I did it, and, like, it sort of works, but, like, I don't think that carts would really... You'd expect them to keep on going, making something that's going the same direction.
Maybe if the one in front was a lot heavier and this one hit it, the lighter one hit it, it would bounce back a bit. We've got a cart system next door. We could go in and try it. All right. Yeah, let's go and see if we can make that happen in a bit. But first, oh no, they're doing an exam in there. Maybe not. Next lesson. All right. So, had enough of that. Who has a recommendation for what I should do first? Read the question though. Kit. What would I do before that? Yeah, what might I even do as well before that? Or just after that? What else don't I like about this question to start the question? Grams. Yes, always look out for grams or tons in a physics question and convert first. So, 0.15 kilograms, isn't it? 0.3 kilograms in it. Okay, now let's define a direction. What would you like for your positive direction?
East.
Shh. Okay, here we go. Now I'm going to do the initial momentum, same as all the other questions. Usually they give you all the information to find initial momentum, then that means you have final momentum, and then you use that to find the final velocity. Rarely they'll give you enough information to find the final momentum, and then they'll ask you to find something about the initial velocity. But it should be pretty clear from the question. All right, anyway, initial momentum is... Now, in this one, we have no coalescing. All right, so we'll go 1 and 2 again. This can be number 1 and this can be number 2. So we've got the mass of the first cart times the velocity of the first cart plus the mass of the second cart times the velocity of the second cart, yeah? Oh, and this is an I. So, therefore, the initial momentum is 0.15 times 0.75 plus 0.3 times 0.25. Now I've checked and they're both east, which means that they're both positive.
0.1875.
Is that the whole thing?
Yes.
What is it?
0.1875.
Okay, I've gone to 3 sig figs, which is a bit naughty because the question's only given me 2, but YOLO. Okay. Now that is equal to what? Fantastic. The final momentum. All right. Now, what's next?
You want to find the how many kilogram meters a second
The momentum of...
cart has at the end.
Okay, yes, let's do it. Let's do it. All right. Shh. 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 Now, because they haven't coalesced, okay, it's still M1V1 plus M2V2. All right? But now we're looking at the final velocities, not the initial velocities. We could have used U up here, I suppose, if you want. Up to you, whatever. All right. Shh. Stop that, Sebastian. Okay. Now, the mass doesn't change, does it? 0.15. And what does it say about that? It's traveling at 0.25 meters per second westwards. So what do I times it by? Negative 0.25. Yes, that is the key. Plus the mass of the second cart, 0.3, times the velocity of the second cart, which is what we're trying to find. And that all equals 0.188. Okay? All right. Now, I'm going to do 0.15 times 0.25, which gives me negative 0.038, two significant figures, plus 0.3 V2. Let's add that to both sides. So it's going to go on the other side. How's you guys' algebra?
Terrible.
Thanks. Now we would divide by 0.3, wouldn't we? So I get 0.75. What is my answer about? Meters per second east. You're trying to trick me again. And we got a positive answer. It'd be pretty scary if they both started moving west after the collision. But none of them are negative in the initial one. Everything's going east. Nah. Yeah. No, well, look, this is what Kit and I were just talking about, but that's why I wanted to go next door and use the tracks, but we'll have to do it next lesson. But if the first one was a lot heavier, and then you threw something small at the second one, faster, it would bounce back, wouldn't it?
I don't think I'd double the weight for this one.
Maybe. Let's try it next lesson and see what happens in theory. In practice, I mean, not theory. That'll be fun. Alrighty, mighty. That's the last example. We've done all the momentum examples. So I'm really pleased that you paid attention so nicely. And we got through all of them. Now we need to practice these. They really do need a lot of practice. So let's go to our physics books and do the examples from our physics books, please.